a little bit, and we're going to discuss a subcomponent of trigonometry, of geometry, and that is trigonometry. Trigonometry has a little bit more of a complex sounding name than just plain old geometry. It is a little bit more complex, but not really much more complex. We're going to discuss some basic rules. We're not going to go into in too much detail. I will tell you that if you ever go on, has anybody here ever studied calculus? Calculus kind of builds on all three of the basic math subjects, geometry and algebra and trigonometry as well. So if you ever do calculus, or one day if you ever learn calculus, which you might not, but if you do, trigonometry will become a very important component of it. You'll need algebra, of course, you'll need geometry, of course, and you'll need trigonometry as well. Trigonometry is really a study of the characteristics of the relationship between the angles of a triangle and its sides. Okay, maybe she'll be around a little while. We'll see. Trigonometry, well, really for the first half of today's class, everything we're going to discuss applies specifically to right triangles. However, there are some trigonometric functions that apply even when you're not talking about right triangles. Okay, so there are three basic functions that I want to discuss. There are actually 6 functions, but only 3 that I want to discuss now. The 3 basic functions are the sine function, the cosine function, and the tangent function. First of all, let us draw our right triangle so that we know what we're referring to. And I'm going to try to get this as close as possible to a straight line because it's important that this look somewhat like a right triangle. And, oops. Okay. Okay, I'm sorry. It doesn't exactly look like a right triangle, but we're gonna draw this as clean. Okay, close enough. And we'll have a diagonal that connects these two. Okay, so it's not a perfect right triangle, but it'll have to do. It's the best I can draw in terms of freehand. Okay, let's say this is a right triangle, so you've got a right angle over here. What trigonometry is about, it's looking at the relationship between an angle and the sides of a right triangle. Let's say we talk about an angle, and I'm going to call that angle theta. This symbol is the Greek letter called theta. Generally speaking, when people are talking about angles, they don't know what the degree is. Very often they call it theta. So we're going to use theta just because your book uses theta, and many other people that deal with this use theta as well. The sine of theta, in other words, whatever that might be, whatever angle V, is equal to the ratio of the side divided by the hypotenuse. The cosine theta is the adjacent side divided by the hypotenuse. And of course, I'm going to examples in a minute. And the tangent of theta, whatever that may be, and again, we don't know what that angle is quite yet, is equal to the opposite side divided by the adjacent side. So, for example, let's say this is, first of all, when you're talking about an angle, this would be the opposite side because it's across from the angle. This would be the adjacent side because it's next to the angle. And of course, the hypotenuse is always the side that is from the right angle. So, for example, let us say that the hypotenuse in this case was 5. The opposite side was 4, and the adjacent side is. Okay, so who can tell me what is the sine of theta? Sine is the opposite side divided by the hypotenuse. So, what's the sine of theta? based on this triangle over here that I have over there for you? Well, the opposite side is 4, so we're going to put that on top of the fraction. And the hypotenuse is 5, so we're going to put that on the side of the fraction exactly. So our answer is going to be 0.8 because that's 4 divided by 5. Excellent. What is the cosine of theta going to be? Well, the adjacent side is 3. The hypotenuse, once again, is 5. So this time it's 3 divided by 5 and 6. And then you have the tangent of theta, which is opposite, which is 4, divided by 3, which is 1 1/3. So we'll call it 1 point. So those are the relationships between them. And the reason why this is important is because if you know the sine or the cosine or the tangent, you can then turn around and figure out what the angle is, what the angle of theta happens to be. We don't know what the angle is yet, but using trigonometry, we can find it out. And actually, let me get to that in a minute. The way you can figure it out, in the old days, when I was in high school, we actually had a book, and in the back of the math book there was a table that told you the sine, cosine, and tangent of all angles from 0 to 90 degrees. Obviously, theta has to be above 0 and it has to be below 90. It can't be 90 because the triangle already has a right angle, and then that would equal 180. That wouldn't leave anything for the third angle. And it can't be 0 because no such thing as a 0-degree angle. So it had to be between, let's say, between a little over 0 and a little under 90, and we would actually look up the numbers that apply to the particular angle. Today you don't need that. Today, if you happen to have a calculator, does anybody have a calculator handy, a scientific calculator, one with trigonometric functions? If you have one, you probably have a sine, cosine, and a tan on the calculator. What I'm going to do is I am going to show it to you on a site that I happen to find, and these sites are available all over the place. So I am going to give you this link over here. No, 1 second, that's the wrong one. Okay, can everybody see this? This website I got over here, this trigonometry calculator website that I have. Okay. I'm going to give you the link, by the way, if you want to use this a little bit later on. You can use it as well. Okay, so in order to figure out, this is very similar to the buttons on the calculator. If you want to figure out what the sine of a particular angle is, let's say we want to know what the sine of a 30-degree angle is. So I can put in 30 and press sine, and it will tell us the sine of 30 degrees is 0.5. Don't worry about radians; that's something a little different. But the sine of 30 degrees is 0.5. Let's say I have a 60-degree angle. The sine of a 60-degree angle is 0.86603. The sine of an 89-degree angle is almost 1. Not quite 1, but almost 1. The sine of a 1-degree angle, a very small angle, obviously is going to be a very small number. Now, if you know the ratio and you want to know the angle, well, then you simply have to use the inverse function. And on this website, it's with this function, the arcsine, which is really the opposite of the sine. So getting back to our example, actually, let me open this and bring our example here. I'm gonna let me make this a little bit easier for everybody to see. Okay, so can everybody see it now? You should be able to see the same browser as we saw a little while ago. Okay, good. All right, very good. Okay, so in our example over here, we had our sine was 4 divided by 5, or 0.8. So what I'm going to do is input 0.8, and I'm going to press arcsine, which will give us 53.13 degrees. That means this angle, according to the sine ratio, is 53.13 degrees. Now, of course, if we do the cosine ratio, it had better give us the exact same result. Otherwise, we got a problem. So let's put 0.6 and put in arc cosine, and lo and behold, we have the exact same result. Obviously, it had to be the exact same result because it's the same triangle. It's the same everything. We didn't change anything. The angle obviously it hasn't changed. Now let's do the tangent. The tangent was 1.333333 is 1.3 bar. And then if we press the arc tangent, in other words, we're looking for the tangent angle that will give us this ratio, it'd also be the same. And of course, it is 53.13. No matter what we do, obviously, it's always going to be the same. Okay. On a calculator, you would have the same. There, do you see the number? On your calculator that you have in front of you? Do you have a sign button? If you have a sign button on your calculator, okay. So if you have the angle and you want to know what the ratio is, then first press the angle and then the sign button. You know, I want to know if there's a. Let's see. What do you have? A TI-84? Let's see if we can find a TI-84 emulator so I can show you how it works. TI-84 emulator. Actually, no, it's going to make us download it. Well, Windows probably has a scientific calculator utility somewhere, right? No, interestingly enough, there's no scientific functions there. So how about Google? Google probably has one. Oh, there we go. Okay, good. So Google actually has the sine function and the cosine function as well. So the same thing. So for example, if we have, let's say 30 degrees, and we press sine, so it's going to give us. Actually, no, I'm sorry. So Google thing works a little bit differently. So the Google one works a little differently. So here we want the, let's say, the sine of 30 degrees, and that's going to give us. No, 1 second. All right, never mind. This one looks a little different. Yeah, it's there. Yeah, then you got it right. If you got 0.5, then you're doing it right because the sine of 30 degrees is 0.5. If you want to do the opposite, should we download this? Octopus deploy. All right. Well, anyway. No, it's not letting me download it. All right, whatever. Anyway, so I'm sorry, I don't have a calculator emulator in this computer, but yeah, okay. And the way to do the opposite, this is Windows 10, so maybe I just didn't have the right app. Okay, whatever it is. The point is, if you have, if you want to get the opposite, in other words, if you have the ratio and you want the angle number, so there should be an inverse sign, like maybe a sign with a little -1. Christine, do you see that on your calculator? Do you see like a sign with a -1? Okay, now there must be an inverse or a function button somewhere on the calculator. So if you use that function button or the inverse button, it will give you give you the arc sign. In other words, it'll give you the if you give the number, it'll give you the angle. So it's kind of the opposite way of doing it. Okay, great, excellent. Glad I was able to explain that without a calculator in front of me. Although I have a feeling you've figured it out pretty much yourself. All right, okay, fine. So that's how to use the ratio. What if you have the opposite? What if you have a triangle, and you have the angle, but you don't have the sides. You don't have the. Then you use something very similar. Let's say you have a triangle, and I'm not going to worry so much about getting this precise in terms of the drawing. We're just going to draw it very roughly. All right. So let's say we've got something like, let's say, 30 degrees. Let's say we know this is a 30-degree angle, and we know that this is 10. Okay. Now, if this is 10, And we can actually figure out both other sides. Now, the Pythagorean theorem won't get you home over here. The angle is 30. That's 30 with a little, like I meant it to be like this. But sorry, it came out as that looking like a 0. I don't know why it's not letting me draw this very well. All right. Anyway, so it's 30 degrees. So we want to figure out the hypotenuse and the other leg. Now, of course, if we had two of them, we could just use the Pythagorean theorem. We don't have two of them. So we can use the sine formula, or we could use the cosine formula. I'm sorry, we can't use the cosine formula because we don't have the adjacent or the hypotenuse. But we can use the sine formula, or we could use the tangent formula. Let's use the sine formula. Sine of theta is always the opposite over the hypotenuse. Now, in this case, what's the sine of 30 degrees? Well, we just figured it out a little while ago. The sine of 30 degrees is 0.5. Just to make sure, I'll put 30 degrees, and the sine of 30 degrees is 0.5. Okay, so we're going to put a 0.5 over here. Equals the opposite, and we'll plug it in. So the opposite side was 10 over the hypotenuse. And we don't know what the hypotenuse is, so we'll just call it x. Now here we just simply solve for x, and this is really a ratio. 0.5 is really the same thing as 0.5 over 1. Anything is really the same thing as itself over 1. So here, to get a ratio, we can cross multiply. 0.5 times x is 0.5x equals 10 times 1, which is 10. Divide each side by 0.5, and you have x equals 20. Okay. So we know that the hypotenuse is 20. Now, once we have this, how can we figure out the third side? Well, the third side we can figure out a whole bunch of different ways. We can use the Pythagorean theorem. We can use the cosine, we could use sine, we could use tangent. We can use pretty much anything we like. Actually, I'm sorry, not sine, because sine is opposite over hypotenuse, but we can use tangent, because tangent is opposite over adjacent. We can use cosine, because we have the hypotenuse, so we can really use any of these ratios. Let's use the tangent ratio, just for kicks. So it's the 30 degrees. We want to figure out the tangent ratio. Tangent ratio is 0.577. We'll round it off to. So we'll say 0.577, and tangent is opposite over adjacent. So 0.577 is 10 divided by x, because we don't know what x is. No problem, welcome. And so we can then cross multiply once again and say 0.577x equals 10. And what's 10 divided by 0.577? Well, I'm going to do it on my calculator over here. 10 divided by 0.577 is approximately 17.33. Okay, so we'll call this 17.33. Good. Okay, so, and of course, if we were using the cosine ratio, we'd get the same thing. What's the cosine of 30? Well, the cosine of 30 is approximately 0.86. Plus 866 equals the opposite, adjacent over the hypotenuse, and we didn't know what the adjacent was, so we'll call it x, and the hypotenuse was 20. And then we could cross multiply and say x equals 20 times 0.866. What's 20 times 0.866? Well, 17.33. I could see it right away. 0.866 is 8.8 and 2/3. So if you multiply that by 20, you're going to get 17.33. Either way, or if you do the Pythagorean theorem, that would be 10 squared plus x squared equals 20 squared. So x squared is going to equal 300, and the square root of 300 is approximately 17.33. Any way you slice it, you're going to get the same answer. All right. Let's look at the slide once again. And these are the ratios, and a trick that I remember learning about in 11th grade or whatever, 9th grade or 10th grade or whatever it was. The quote-unquote SOHCAHTOA trick. Anybody ever heard this one before? SOHCAHTOA is a way to remember the three main trigonometric functions. Sine is opposite divided by hypotenuse. Over the hypotenuse, and then CAH is CAH, which means the cosine is the adjacent over the hypotenuse, and then TOA is the tangent equals opposite over adjacent. There are three more trigonometric functions that are simply the inverse, or the three possible leftover ratios. Hypotenuse over opposite, hypotenuse over adjacent, adjacent over opposite. Those are the cosecant, the secant, and the cotangent. I'm not going to worry about that right now. You're not going to need that for this particular course. If you ever learn calculus one day, you ever take a calculus course, you will become very familiar with cosecants and secants and cotangents. They will be as important as sine, cosines, and tangents. But the point is, for regular plain old trigonometry, you don't need them. Remember, if you have the sine and the hypotenuse, if you have the opposite and the hypotenuse, you can use the sine. If you have the adjacent and the hypotenuse, you can use the cosine. You have the opposite and the adjacent, you can use the tangent. Those other three ratios are simply the reverses of these first three functions. So for purposes of regular trigonometry, you really only need these three functions, and that's why we're going to focus only on these three functions. Okay. Some of the other things that you can do with trigonometry is you can use trigonometry to calculate the area of a triangle. The altitude of any triangle means the height of a triangle. And the way you measure the height of a triangle is you take the top angle and you shoot an altitude down straight to the bottom side. And the altitude always makes a right angle. If you may recall, hopefully you do, the area of a triangle is the base times the height divided by 2. Now the base, in this diagram, for example, is simply BC. Okay, sorry, for sine and tangent, are the sides always the same place? Well, no, because the sine is the opposite over the hypotenuse, and the tangent is the opposite over the adjacent. So they both use the opposite. They both use the opposite on top of the fraction. But the tan uses the adjacent side in the bottom of the fraction, and the sine uses the hypotenuse underneath the fraction. So yeah, they always start with the same thing. Sine and the tangent both start with the opposite side, but they use something. Their ratio is a little different in the bottom of the fraction. Okay, so if you take a look over here, so this would be an example. Let's say we managed to figure out B and A, or A and B. That doesn't necessarily tell us what the height of the triangle is. To do that, we may need to use the trigonometry. Well, it always corresponds to whichever angle you're looking at. It can be done with any angle, as long as you look at the angles that correspond to that particular side. You know, we're going to get to some practice over here. I know it's a little confusing, but we're going to get to some practice a little bit, and hopefully that'll clarify things a little bit. All right, let's take an example over here. This is our first practice example of the day. Find the area of the triangle and side marked X. Okay, so we need a plan over here to start with. First of all, just using the Pythagorean theorem is not going to work, because we don't know, there's no right triangle here that we know two of the sides. In a right triangle, if you use the Pythagorean theorem, but you need two of the sides to use that. Over here, we have NP is 9. We have AN is 3. But in order to get the area of the triangle, we're going to need the base times the height divided by 2. Now, in our case, the base, what's the base of this big triangle? ANP, or NAP, NAP. What's the base of triangle NAP, of triangle NAP? The base is side, right, is 9, exactly, and T, and if you want to use the The official name for it really should be NP. Okay, NP, 9T, whatever you want to use it. And the height over here, of course, is going to be AT, because that's the altitude in this case. Okay, good. Now, we don't know, of course, what NT is, and we don't know what NP is. If we do, we can then use the Pythagorean theorem to figure out what we need to figure out. Okay, so how do we figure out AT to start with? Or NT to start with? Well, let's use trigonometry. Which one do you want to go for first? Do you want to go for AT or do you want to go for NT? Doesn't matter which one, so I'm just going to pick whichever one the first person says. Okay, NT. We're going to go for NT first. Okay, for NT, which function are we going to utilize? Which trigonometric function are we going to utilize? The problem is we can't use the sine because the AT is the opposite, and we need the opposite for a sine. For cosine, we have the hypotenuse. The hypotenuse of this triangle over here is AN, and NT is the adjacent side. So we're going to use the cosine function because that's the adjacent side. Cosine is the adjacent divided by the hypotenuse. Okay, so what is the cosine of 50? Well, I'm going to, you can use it on a you can figure out, if Christine can do it on her calculator. If you have it, I'm going to do it on my thing over here. And according to my calculator, according to my thing that I still have open in the other window, I have the cosine of 50 being 0.643. We'll round it off to 0.643. 0.643, which is the cosine of 50 degrees, okay, this is the cosine of 50 degrees, equals the adjacent. We don't know what the adjacent is, so we'll call it x. And what are we going to put on the bottom over here? 3. Good, because that's the hypotenuse. So then you cross multiply, so you got x equals 0.634 times 3. What's 0.634 times this 0.6? Actually, I'm sorry, I made a mistake over there. Instead of being 634, it should actually be 643. I inverted those numbers. So I'm going to say 0.643 times 3, and you get approximately 1.93. Okay, good. We're around 1.9. So we know that this side is 1.93. Okay, once we have that, now we can figure out AT using the Pythagorean theorem or using a trigonometric function. Let's do AT using a trigonometric function. Which one do you want to use? And we could use any of them, by the way. Let's figure out AT. We can use sine, we could use cosine, we could use tangent. So which one do you want to use? Okay, fine. Let's use tangent. Good idea. So the tangent of 50 degrees, opposite, which is x, is that's what are we going to put on the bottom? The adjacent side. What's the adjacent side? .93. Very good. Okay. What's the tangent of 50? I've got approximately 1.19 equals x over 1.93. So let's do 1.93 times 1.19, and you get approximately 2.3. Yeah, almost exactly 2.3. So we're going to make this rounded off to 2.3. Okay, so how do we figure out the area? Well, for the area is base times height divided by 2. What's the base? Okay, so the area is 9 times 2.3 divided by 2. Okay, so 9 times 2.3 divided by 2, and I've got approximately 10.35. So the area of the entire triangle is approximately 10.35. Okay, what about x? How do we figure out what x is? Well, again, we could use the Pythagorean theorem, because we know that if the whole thing is 9, then pt must be 9 minus 1.93, so pt must be approximately 7.07. Or we can use well, actually that's pretty much the only way we can do it, because we don't have any of the other angles. So the only way we could do it is the Pythagorean theorem. Okay, so we've got 2.3 squared plus 7.07 squared equals x squared. Now, 2.3 squared is 5.29 plus 7.07 squared, which I think is going to be close to 50. Almost exactly 50. 40, really, well, yeah, basically 50. 50 equals x squared. Add them up. And take the square root of that, and it's about 7.27 approximately. So x is going to be about 7.27. So, okay. So we figured out what all the lengths, what all the sides were, and if you used any trigonometric ratio, we could now figure out what angle p is. If we want to know, let's figure out what angle p is, just for kicks, just for fun. Let's figure out what angle p is. All right, how do we figure out what angle p is? Well, let's figure out its sine, its cosine, or its tangent. Doesn't matter which one. Exactly. Which one should we use? Doesn't matter which one. I'll use anything, whatever somebody volunteers first, we'll use. Okay, let's use the sine. So fine, the sine of p equals, sine of angle p equals the opposite, which is 2.3, divided by the hypotenuse, which is 7.27. What's 2.3 divided by 7.27? All right, I've got about 0.316. So the sine of p equals about 0.316. Okay, so let's go back to our this up here. Okay. Okay, I don't know what happened there. I guess I must have, when I was trying to minimize something, I must have pressed the X instead of the minimization button. All right, but anyway, I'm back. So this time you're just going to have to trust me on the. Let me get that link. I think I closed down that link as well. All right. Okay, fine. So where were we? We had, okay, so we had 0.316. So I'm going to put in 0.316. Then I'm going to push the arctan button, and that tells us that P is approximately 17.54 degrees. Anybody else get that? I don't know if anybody else was doing it with me, but hopefully if you were doing it when I left for a second over there, that should be what you got. Okay, does everybody understand that? Okay, we good? Okay, fantastic. All right. Two more quick things. This one has nothing to do with right triangles. These last two rules work with any kind of triangles. And they're very important because the fact they work for any kind of a triangle. And that is, even with a regular triangle, the ratio of the sides to their sines works with any two sides. So let's say this is angle A, and this is, let's say this is side A, this is side B, this is side C, so we'll call this angle B and we'll call this angle C. So the ratio of an angle, of the sine of an angle to its opposite side is the same for every side of the triangle. So for example, the sine of A divided by side BC, which is the opposite of side A, is the same as the sine of angle B to AC, which is the opposite side to angle B. And the same thing is true, of course, for the third side. It's also equal to sine C divided by the length of side AB. So, for example, if I told you that this was, let's say, 70 degrees, and this was 10 inches, and I told you that this was 50 degrees, and I wanted to know how many inches is this? How many inches is AC? Well, we could do this with a simple ratio. We could say the sine of B is to x, because we don't know what x is, as the sine, and B of course is 50 degrees, that's this to this, is equivalent to the sine of 70 degrees to 10, because that's this angle and this side. In other words, the function works appropriately. And of course, then you would just go ahead and figure out what the sines of each side are. So let's say sine of 50 is 0.766. So I would turn this into 0.766 divided by x equals the sine of 70, which is 0.94 is to 10. And then you'd cross multiply, so you'd have x times 0.94 equals times 7.766, which is 7.66. So you'd take, then you would divide each side by 0.94. And okay, what's 7.66 divided by 0.94? Do it in your calculator. It would be like, I guess about 6.7 or 6.8. 7.66 divided by 0.94 is going to give you, well, actually a little, yeah, that's right. It's going to give you 8.15 approximately. Going to round it up to 8.15. So this side, x, is going to be approximately 0.15. Notice, of course, by the way, that the bigger the angle, the bigger the opposite side. That's what's going to happen with any triangle, no matter what. The bigger the angle, the bigger the opposite side is going to be. Okay, that's the law of sines. The law of cosines I'm not going to just go into. I'll show it to you because it's there. It's there in the textbook. There is also a relationship between the cosines of an angle, and the relationship is as follows. A squared, which is the the side squared equals b squared plus c squared minus 2bc cosine a, etc. I don't even want to worry about that necessarily. I just brought it in there because it's in the textbook. But that's also a relationship between the cosines of the sides, in addition to the rules regarding the sines. Okay. Now, with that in mind, let us look at some examples over here. Okay, I'm going to try to screen share this again. I hope I don't end up getting thrown out of the classroom again, but I'm going to try to avoid doing that. But if I do, you'll know what happened. Okay, can everybody see the browser in the upper and the lower left-hand corner of the page over here? All right, here we go. Okay, let's try to figure out these answers. And then in about 10-15 minutes or so before the end of class, I want to look at one of the homework examples, which I thought was a trigonometry question. It really isn't a trigonometry question. Okay, a ladder leans against a building. The foot of the ladder is 6 feet from the building. The ladder reaches a height of 14 feet, excuse me, as you can see. Find the length of the ladder to the nearest foot. Okay. First of all, how can we figure this out? Do we need trigonometry, or actually, can we use trigonometry? The answer is no, because we don't know what the angles are. We know that this is a right triangle. We know that this building goes straight up, so the building with the ground is a right triangle. So the only way to get the length of the ladder is the Pythagorean theorem. That's correct. How would I use the Pythagorean theorem? Well, the Pythagorean theorem is a squared plus b squared equals c squared. Now, a in this case would be, let's say, 6 squared. The c is always the hypotenuse. Plus b squared, we don't know what the ladder is, so we'll call the ladder x squared, equals c squared, which is 14 squared. And, let's see. Okay, so it could be 36 plus x squared equals 14 squared, which is, what, 196, I believe. So that means x squared equals 160. And he said the square root of 160 is about 15.23. Okay. No, that can't be. No, that has to be 12 point something. Yeah, the square root of 160 has to be about 12.5 or 12.6, give or take. 160, square root of 160, yeah, 12.65. Okay, good. Okay, so this is 12.65. That's the length of the ladder. The ladder has to, and of course the ladder has to be less than 14. I'm sorry, that doesn't make sense either. So what did, you know what the problem, what mistake did I make? What mistake did I make? Well, the 160 was 196 minus 36 to isolate the x, but I made a mistake. What mistake did I make in doing this problem? Did anybody catch the mistake? What did I put as the hypotenuse? I put the wall as the hypotenuse. I put the 14 as the hypotenuse. What's actually the hypotenuse? The ladder's the hypotenuse, right? It should have been the ladder that's the hypotenuse, exactly. So let's do it again, this time properly. So this time we'll put 6 squared, which is one side, plus 14 squared, which is the wall, equals the ladder squared. Because the ladder's the hypotenuse. So 6 squared is 36, plus 14 squared is 196. Equals x squared. Okay, 36 plus is 232 equals x squared. And so x equals the square root of 232. And yeah, that makes sense to be about 15.2. So yeah, 232, the square root of that is 15.23. Very good. Okay, excellent. So this is 15.23. Excellent. Okay, so now that we have that, so we're going to fill in this. To the nearest degree, Oh, to the nearest foot. Okay, they asked for the nearest foot, so it's 15. Fine, okay. All right. Find to the nearest degree the angle that the ladder makes with the ground. How do we do that? No problem. Enjoy. Okay, so how do we do that? How do we figure out to the nearest degree the angle the angle that the ladder makes with the ground? This angle over here. Well, really, we can use any trigonometric function, right? Which trigonometric function should we use? Doesn't matter which one, we can use. Fine, let's use cosine. Good. Okay, so cosine of theta, we don't know what it is, so we'll call it theta, equals the adjacent over the hypotenuse. What's the adjacent? To this angle over here, that where the ladder meets the ground. What's the adjacent side? Not 15. That's the hypotenuse. The hypotenuse is 15.23. The adjacent is the one that's not the hypotenuse. That's next to the angle. So that would be the 6. The hypotenuse would be the 15.23. So now we can figure out that cosine of theta equals 6 divided by 15.23. Let's do that in a calculator. And that comes out to approximately 0.39. Okay, good. Sure, no problem. We'll go to the homework. In fact, there's another one in the homework that I want to look over. But sure, we can look at number 1, and then I want to look at number 5 a little bit from the homework as well. Okay, so 0.39. How do we figure out what's the angle? Well, let's go back to our calculator over here. Let's put in 0.39. And since we're figuring out the cosine, we're going to put arc cosine, and arc cosine is approximately 67.046 degrees. So going back here to the nearest degree, so that would be about 67 degrees. There we go. All right, let us look at the homework. Just a couple of examples from the homework that I wanted to discuss. Question number 1 from the homework. How are we going to figure this out? In ABC, if angle A is 50 degrees, and A is 10, C is 12, find angle B, angle C, and little b to the nearest tenth. How are we going to figure that out? What rule are we going to use? Let's get this on a Microsoft Paint. Whoops. No. Sorry about that. Let me make it a little bigger so that you can see a little bit. Whoa, this is a little too big. Let me get that a little smaller. Close enough. All right. Can everybody see this? Does this work for everybody? Okay, good. Sorry, it looks like somebody sat on the diagram. All right. Okay, so we've got angle A is 50 degrees. Okay. Side A is 10, and side C is 12. And we want to know angle B, angle C, and side B. How are we going to do this? Who can give me an idea of which rule are we going to use? Which law are we going to use? How about the law of sines? Can we use the law of sines over here? That's right. We can remember at the end we got the ratio of a sine of an angle to its opposite side applies to everything. So we can use this, A and its opposite side, and C and its opposite side. So let's say we're going to use A is to sine A as C is to sine C. Well, we know what side A is. That's 10. Do we know what Sorry about that. How long was I out for? Did you hear? Did you hear what I was? I just got. Okay, good. Okay, very good. I'm glad I wasn't out for very long. I just had a little bit of a connectivity issue. I don't know what happened. The thing is, I'm draining the resources of this of this by doing all this screen sharing and all this drawing and everything. So I think that's why we're having a little bit of a connectivity issue sometime. Okay, so this side was 10. Good. Now, how do we figure out what the sine of A is? Well, A is 50 degrees. I don't know. Yeah, I think that's normal. I think that's just in the way the system works now. But I think that's just because I'm speaking. Okay, so we have to figure out what's the sine of 50 degrees. Well, let's get this back. The sine of 50 degrees is 0.766. Okay, so we'll put 0.766 over here equals C. What's the side C? Does it tell us what side C is? 12, good. Is to sine C, and we don't know what that is, so we'll call it X. So now we'll cross multiply. 10x equals 12 times 0.766 equals 9.19. 2. Let's divide each side by 10. So x equals 0.919, we'll call it. That means the sine of C, really x is the sine of C. That's what we converted. We took sine of C and made it into x, so we can change it back to the sine of C equals 0.919. Well, let's figure out what is the sine of 919. And let's get back up our browser calculator there. Okay, what was that? 0.919, I think it was. 0.919. And we'll use arcsine to figure out what the sine is. Yes, that's correct. 66.78 degrees. Excellent. So that means C is 66.78 degrees. So we'll mark that 66.78 degrees. Okay. Well, now we've still got to get B and angle B. Well, how do we do that? Well, we don't yet know either side B or its angle, so we can't use the rule of sines just yet. But is there any way we could figure out the angle B? Forget trigonometry. Just basic geometry rule. Something that we learned way back, who knows when, like a month ago. Well, all the angles of a triangle have to equal 180, exactly. Okay, so let's take 180, and we'll subtract 50 from angle A, and then we'll subtract 66.78, and now we've got 63.22 left. Okay, now we've got one last piece of the puzzle, and that's side B. What would we use to figure that out? Well, you can use the rules. You can use the rule of sines again. And this one I'm going to let you do by yourself for the last piece of the puzzle. Let's just use the same thing. Use sine B is to sine of 63.22 as sine 50 as 10 is to sine 50, or you can use either one, by the way. You can use B is to sine B as C is to sine C, or as A is to sine A. Either one will get you the correct answer. All right. The next one that I wanted to look at in the homework I thought was a very interesting problem. And when we were looking at it during one of the classes, I told you that I thought that you needed trigonometry to solve it. But I think as I was looking at it again, I realized that you actually don't need trigonometry to solve it. So let me zoom in over here and see. I don't know why it gives me such a big picture here. All right. There we go. Okay, so we got this. Did anybody try this one, by the way? Anybody look at these? Okay, fine. If you haven't, that's fine. Also, okay. So now, we have to figure out the length of the wire. Basically, the wire is A to B to C to D. So we got to figure out all those three. Anybody have any ideas to start with? What can we fill in to start with? Okay, AB. How do we get AB? Pythagorean theorem. Good. Anybody know what AB is? What side AB is? This is one of those special triangles. This is one of those three types of triangles. Remember the three types of triangles? 3, 4, 5, 8, 15, 17, and the middle one was? Anybody remember? There was the 3, 4, 5 triangle. And this one, well, there was the three types of triangles were the 3, 4, 5. There was the 5, 12, 13, exactly. 5, 12, 13, and 8, 15, 17. Now, if you wanted to do the Pythagorean theorem, the Pythagorean theorem, 5 squared is, just very quickly, just to do the Pythagorean theorem, a squared plus b squared equals c squared, so 5 squared plus 12 squared equals c squared. 5 squared is 25, plus 12 squared is 144 equals c squared. That's 169 equals c squared, and I don't know why it's... Okay, 169 equals c squared, and that makes that 13. Okay, what's next? How else can we work on this? I can tell you right now, there is a hard way to do this by what we discussed today, trigonometrically, and there's an easy way to do it based on what we learned on Monday. First of all, which one do you want first? Do you want to try to get CD first, or do you want to try to get BC first? Let's try to get CD first. I think CD is going to be a lot easier, yeah. Okay. So that's my hint to you. My hint to you is that there's a hard way to do it using trigonometry, and there's an easy way to do it using what we learned on Monday. What did we learn about on Monday? On Monday we learned about similarity and similar triangles. Now, are these triangles similar? No. What is it? That Phil that Phil has you know what I'm going to do? I think I know what I can do. If I draw these, I think that'll I think that will. Okay, that's what we need. Maybe that'll let the maybe. No, I don't. Okay, I don't know. Okay. All right. This triangle, I don't know why it's not letting me fill it once, but these two triangles, the two light purplish triangles, pretend they were totally filled in. Are they similar triangles? The answer to that is yes, they're similar triangles. Why? Because they've got two equal angles. What are the two equal angles? Angle A is equal to angle D, as Gina said, that's correct. And also that these two angles are right angles. This is a right angle and that's a right angle. So because they've got two equal angles, they're similar. What do we know about similar triangles? Their sides are in proportion, right? So that means the 5 is to the 7.5 as the hypotenuse is to the hypotenuse. So we can use that ratio. We can say the 5 is to the 13. In other words, this is to this, as this is to this, because they're corresponding sides of similar triangles. So we'll say as 7.5 is to x. And now we can cross multiply, which gives you 5 times x, which is 5x, equals 13 times 7.5, which is 97.5. Good. 97.5. Divide each side by 5, and you've got, I think, 19.5. Yeah. Okay, good. So x is 19.5. Okay, so now we've got this as 19.5. So we're 2/3 of the way there. Now we got to get BC. How can we get BC? How indeed can we get BC? Okay, draw another triangle where? Good, that's a very good strategy. Draw. I know it's hard for you to describe it because because I'm the one with the pen. With B straight across. Excellent description. I agree with that 100%. Let's draw another triangle. Take this triangle and draw it straight across. Remember, you can do this. You can draw it. If you were to draw this triangle, what sides do you know? Well, do you know? Let's give this a random number. Let's give this side E. Let's call this point E. Do we know BE? Well, sure, BE. Really, this is a rectangle. This thing in the middle over here is a rectangle. Not only is it a parallelogram, it's actually a rectangle. So opposite sides are equal. So this is 15, good. What is EC? How would we figure out what EC is? Not so simple. We have to know, let's put another point over here. We have to know FC in order to get EC, but can we get FC? Okay, well, we can use the, basically we can use the, what's it called? We can use the fact that the two outer triangles are similar as well. So if we're trying to get FC, let's try the ratio between FD is to FC. This is to this, as this is to this, as 5 is to 12. Do you see why that works? Because they're corresponding sides of similar triangles. This to this, as this to this. And we know FD is 7.5, so we can say 7.5 is to x as 5 is to 12. And then 5 times x is 5x. 12 times 7.5 is 90. So x equals 18. So if the entire CF is 18, what does that make CE? That makes CE 6, right? Because this has to be equal to this because they're opposite sides of a rectangle. Now, once we have this, how can we get BC? Well, then we can use the Pythagorean theorem. That's right. And then we've got 6 squared plus 15 squared equals x squared. 6 squared is 36 plus 225 equals x squared. 36 plus 225 is 261 equals x squared. Right. In other words, you're talking about to get CF, yes, which is really the same thing. In other words, what you're saying is everything in the purple triangle on the right is 1.5 the size of everything in the purple triangle on the left. Well, yeah, I mean that's the same thing. It's really the same thing as doing the ratio. You found a shorter way to do it, but yes, that's the same thing. Okay, what's the square root of 261? Okay, the square root of 261 is about 16.16. We'll round it up to 16.16. Okay, 16.16. And now, to get the length of the wire, just add them up. And away you go. So yeah, so you didn't actually need any trigonometry on this. You know, what would the harder way be? The harder way would have been to not use the similar triangle rule. To figure out what angle A is using trigonometry, using the tangent. You know, figure out 12 divided by 5. Well, 12 divided by 5 is 2.4. And then once you have the 2.4, figure out what the tangent of 2.4 is. I'm just going to do it on my calculator here. 2.4, and I'm going to use the arctan function. Which is about 67.38 degrees. So then once you figure out A is 67.38 degrees, then you know that D is also 67.38 degrees. And once you have that, then you can figure out the other sides using, using trigonometric functions. So in this one, you could have actually solved it using trigonometry, but you really didn't need any trigonometry. Everything I did over here really has nothing to do with trigonometry. It was all just based on the similarity rules for triangles. Okay, and with that in mind, it's a little after 8, so we're going to stop here for today. And I wish everybody a wonderful rest of the week and a wonderful weekend, and I'll see you all on Monday.